You know, you and I can tell a t-shirt from a shoe in like a split second. But how do you teach a computer to do that? Well, today, that's exactly what we're going to do. We're going to build a simple digital brain, a neural network, to classify images into a bunch of different categories. And trust me, how it works is pretty cool. And really, that's the core question here, right? For us, the difference is totally obvious. But a computer, it just sees a bunch of pixels. So how in the world do we get a machine to find those hidden patterns and learn to tell apart not just two things, but a whole bunch of them? That's the challenge we're diving into. Now, the fancy technical term for this is multiclass classification. I know, it sounds a little intimidating, but it's not. All it really means is that we're teaching the machine to sort things into several different piles, instead of just a simple yes or no. Think of it like a digital sorting hat, but for pictures.
Okay, so to really put our new digital brain to the test, we need a challenge. And in our case, we've actually got two of them. You can think of them as two different digital piles of laundry that our AI has to sort. And believe me, one is a lot simpler than the other.
So first up, we've got the classic MNIST dataset. This is pretty straightforward, just simple handwritten digits, 0 through 9. A perfect place to start. But then we have fashion MNIST. And this one? Oh, it's way trickier. We're talking t-shirts, pants, dresses, sneakers. The patterns are just so much more complex and all over the place. So what makes these datasets so great for this kind of thing? Well, it's all about their structure. Both of them have 70,000 little grayscale images, and each one is just 28 by 28 pixels. And the really important part is that they're already split for us. A big chunk for training our model and a smaller set for testing it. That kind of standardization is just perfect for getting a handle on the basics. All right, so we've got our challenge, our two digital piles of laundry. So what's the tool for the job? How are we going to sort them? We are going to build our own simple digital brain. The technical name is a fully connected neural network, and this is exactly how we're going to teach our machine to start seeing those patterns. To do this, we're going to use Python, along with a couple of really important libraries. You can think of TensorFlow as this super powerful engine that's doing all the heavy math. And then there's Keras, which is like the easy-to-use dashboard that sits on top. It just makes building our network layer by layer way easier. So let's quickly walk through how our network is actually built. It's basically a four-step assembly line. First, we take that square image and flatten it into one long line of numbers. Easy enough. Then we normalize those pixel values, which really just means we squish them into a standard range. This helps the network learn a lot faster. Third, and this is the important part, the data hits the hidden layers. This is where all the thinking happens. And finally, the output layer makes its final prediction, giving us the probability for each of the 10 categories. Okay, let's zoom in on those hidden layers for a second, because this is really the heart of the whole operation. They're packed with these digital neurons, and each neuron has a simple job. It uses a little switch. The technical term is a ReLU activation function to decide if a piece of information it's seeing is important enough to pass along. Now, one of these decisions is simple, but when you combine thousands of them, the network starts to recognize really complex patterns, like the curve of a number 2 or the V-neck on a t-shirt. This is seriously where the magic happens. Okay, so we've set up the problem, we've built our tool, and our little digital brain has now studied thousands and thousands of images. So the big question is, did it work? How well did it actually learn? Let's take a look at the results. Yep. This is the moment of truth. After all that work, after all that training, how accurate is our model? How good is it at sorting images it has never, ever seen before? All right, first up, the handwritten numbers. And the result? A whopping 97.74% accuracy. I mean, that is an amazing score. It basically means our network got it right on almost every single image it was tested on. Fantastic! Okay, now for the much harder test, the fashion items. So how do we do here? We got 88.92% accuracy. Now, like we expected, that's a bit lower than with the simple digits. But honestly, that's still a really solid result. It proves that our network is actually learning to tell the difference between these way more complicated images. And looking at this chart really puts it all into perspective. You can see that performance gap clear as day. That drop of almost 9% from the numbers to the close, it just goes to show you how much tougher it is for a network to tell the difference between things that look kind of similar, like a pullover and a coat, versus the very distinct shapes of handwritten numbers. So, okay, we ran our tests, we got some cool numbers. But let's be real, why does any of this matter outside of this little experiment? Well, let's connect these pixels to the real world. Believe it or not,
The exact skills our network just learned are already all around us. Remember that first test, recognizing digits? Well, that's the same basic tech that reads postal codes on your mail or the numbers on a check at the bank. And the second test, sorting clothes? That is literally the backbone of modern online shopping. It powers everything from how products get sorted into categories to those cool visual search features.
And if we zoom out even further to the really big picture, these same core ideas are what drive much more advanced systems. I'm talking about the pattern recognition that lets a self-driving car spot a pedestrian, or helps a doctor find something unusual in a medical scan, or even lets a big warehouse keep track of its inventory just using cameras. It's the same fundamental principle. So here's the key takeaway, the most important thing to remember. What we built here today, it might seem pretty basic, but its ability to learn and see patterns just from a bunch of pixels, that is the absolute foundation for all of the huge, complicated AI systems that are changing everything around us. It all starts with something this simple.
And that really leaves us with a pretty wild thought, doesn't it? If a simple network, just like the one we talked about, can get this good at identifying complex images, it just makes you wonder, what's next? What comes after this for AI vision? Are there even any limits? It's a really exciting thing to think about. Thanks for diving into this with me.